So here in problem 3.4, the order of the reaction is 1/2 order. If you can recall, we have skipped solving this problem last meeting because I said we will use the empirical rate equation regarding this particular problem, or the formula that we will be getting from the empirical rate equation. So since our order of the reaction is 1/2 order, let's check whether the value that we will be getting is something that is acceptable or not. So let's go to the whiteboard, or let me read first the problem. A 10-minute experimental run shows that 75% of liquid reactant is converted to product by a 1/2 order rate. So your N is 1/2. What would be the fraction converted in a half-hour run? So I'm taking a picture, so I need not go back to this particular document. So let's go to our slide, to our whiteboard, and write down the solution for this particular problem. So feel free to raise your hand or butt in if you have any question or clarification. So I'm writing the solution for number 3.5. So you're given in this problem the order of the reaction. So it's 1/2. And that it's stated that for a 10-minute run, so at t equal to 10 minutes, it says here that 75% of your reactant was converted. Okay? And then it's asking already what would be the fraction converted. So we go to the required. The fraction converted for this same reaction in half an hour run. So at t, so if our time here is in minutes, we might as well express the half-hour run in terms of minutes as well. So that would be 30 minutes. So we will now go to the solution of this problem. Okay? Now, if we will write our rate law, given already the order of the reaction, so that would be the rate being equal to the rate constant and its product with the concentration of A raised to 0.5. That's the order of our reaction. If I will represent this rate in terms of the derivative of CA with respect to time, then I can place the CA here, raised to 0.5, and I will place here the dt on the right side, replacing the negative R sub A by negative dCA dt. Now we will have this particular expression solved. So using power rule, you will have CA raised to negative 0.5. So that would be CA raised to 0.5 minus CAO raised to 0.5 over 1/2. So if it's over 1/2, then this entire thing must be multiplied by 2. I copied the negative. And on the right side, you will have KT being having here the limits 0 to T, by the way, and in here, you will have the limits CAO to CA. So this is our resulting expression. Now, since we are given conversion, XA, there's a need for us to convert here the CA in terms of XA. So we'll go to our next part here, next slide. So we'll have negative 2. I'll change my CA to CAO 1 minus XA, and it being raised to 0.5, so this should also be raised to 0.5. And I have here CAO raised to 0.5. Okay, let me go back and share to you the original equation. So this is it. We change the CA to CAO1 minus XA. This one we copy. And then, of course, we copy what we have on the right side, and that would be KT. Now, since we know that this K this CaO can be factored out, and these two are all constants. So we may as well have them written on one side of the equation, because when we speak of this same reaction, the combination of these products or divisions will be the same. So I will write this K here, I will write here on the left side. So I will have K, this CaO, if it's factored out, so that would be over here. So I will place here CaO. And this -2 will also be over or divided by in here. So this would be -2. So my group of constant would be, or constants would be K over CaO raised to 0.5 times -2. The remaining value on one side of the equation on the left, because I interchange now, would be this. So you have 1 minus XA raised to 0.5 minus 1, which is also raised to 0.5. Okay, now we know that 1 raised to any exponent will be 1, so we can simplify this side to 1 minus XA raised to 0.5, and you have here minus 1. Now the purpose of grouping this thing here is for you to be able to, let's say, get a value for the set value of this given the particular given information for conversion here, which is 0.75 and a 10-minute for the time. So we can do that in here. Your K over -2 CaO raised to 0.5 will be equal to 1 minus 0.75 raised to 0.5 minus 1. Okay, now if you don't want to bring along this particular -2 in here, that would be fine, but you can keep it as well in here. So nonetheless, we will only have the K, let's say CaO raised to 0.5 here, and process this one after you have already multiplied it by -2. So your answer here would be, can you please solve? So you have 0.25 raised to 0.5, or that would be the square root of 0.25 minus 1 times -2. What do you think is the value for the KCAO? K over CaO raised to
Excuse
0.5.
me, miss.
Yes.
Hello, miss. Ang T, miss, nalipatan taguro ang T, miss.
T. All over T. Wait. Yes, I forgot the T. Thank you, Josh. So we will put the T in here. This expression should be over T. Okay, wait. We'll place it here over T. I will place here the negative, and I will have here 1 over T. So this entire expression that you have here should also be placed or multiplied to 1 over T. This one will be divided by T or multiplied to 1 over T. And our time in here is 10 minutes. So we will substitute the 10 in here. So let's say we want only to determine the value of K over the square root of CaO. In this case, there's a need for you to multiply -2 on the other side. Can you please do that? Let's check what will be the corresponding value that we will be getting. So that would be the square root of 0.25 minus 1 times 10 times -2. That would be the value of K over the square root of CaO. What would that value be? Okay. You don't have a microphone or headphone. Okay, so this is
10,
10.
miss.
Okay, 10. Thank you. So if this is 10, Then for the new required information, so I will have here new one. You will have a K over CaO raised to 0.5. I will still have a negative 2 here. I will still have a 1 minus XA raised to 0.5. And I will have here 1 raised to 0.5 because this is our formula on the other side. This expression, by the way, should be divided by T. Now, the purpose is this time we will find the XA. So, the value of the K over the square root of CaO that we have here, we will now substitute, and that would be the 10. And I will have here the negative 2. The time that's given here for us to determine the XA will be half an hour, or that's 30 minutes. So, we will place here over 30. And you will have here 1 minus XA. This is the thing we're looking for, minus 1. Now you will have, surprisingly, a value of XA, which is not valid. Can you please give me the answer for the X? Miss 0.1 siguro because 1 over T. Wait. It's 1 over T. Yes. Okay. So this is 1 over T. So we will divide our answer here by 10. So the value is 1. The new set of value for, so if it's 1 over T, what's the new set of value for, so we will divide by T, so that would be a 1. The K, CA, CaO raised to 0.5. The T here is 1 over T. So it should not be multiplied by 10, but rather divided by 10. So what's the value that you are getting here? It's 1?
0.1, yes.
0.1. Okay. Why is it 0.1? When we multiplied by 10, the answer is 10. When we divide by 10, that should be 1. Is it 0.1? So you have the square root of 0.25. We subtract 1 from that. We divide by 10. And we multiply by negative 2. So it's 1 over 10. Okay. Okay, so this is 1 over 10. If that's 1 over 10, if we go to the next slide, this would be 1 over 10. Okay? And if it's negative 2 over 10. So I think I have written it this time correctly, the equation. So what's the value of XA that you're getting? This time? So you have a 3 divided by negative 2 plus 1. We square that, and then we subtract 1. Is it negative 0.75?
Yes, miss.
Okay, so your answer is negative 0.75. So you may wonder why this is a 0.75. Now, if you recall in the given for the empirical rate equation, that it's possible that for orders less than 1 in the empirical rate equation, the reaction, you will not be able to determine the time. So let me go back to the slide so you would see. I chose this so that I can explain this particular generalization here. So if the order is less than 1, reactant concentration will fall to 0 and then become negative at some finite time. So your answer is not valid anymore because the order of the reaction that we had is less than 1, and that's 0.5. So there's a need for you. So I really did not check based on this formula whether the time that is given in the problem goes beyond or is equal to this one. So now we will check whether this particular generalization here is really valid for this particular problem that we have processed. So we go to our whiteboard. It says that the time for CaO raised to 1 minus n over 1 minus n times k should not be greater or equal to this set value. So let's say, for example, we will solve in our case, what's the t? So your CaO, you don't know the same thing with k, but you know that your CaO, your k over CaO raised to 1/2 is this particular value. Only it's the reciprocal. What I'm trying to say is this. So you have, I'll write here 1 over 1 minus n, and you have here k over CaO, that's 1 minus n, so 1 minus 0.5 is 0.5. I literally place this one, this expression, here in the denominator so that you would see. So your time should not, in this case, should not be equal to or greater than this value. So you have 1 over 1 minus 0.5 times the value that we got for this, the k over the square root of CaO, which is 1 over 10. So this is 0.10. So this time is equal to, so you have a 0.5 times a 0.1, and you take the reciprocal of that, that would be 20. So that minutes tells you that after 20 minutes, your reactant is already fully converted or it's already fully consumed. The problem is asking us for conversion at 30 minutes, or that's half an hour time. So this particular answer is actually valid because we did not do the checking. So it's important that you do the checking. So in this case, even though this is the answer that you got, you are still going to answer XA is equal to 1.0. And you're going to validate that answer using this particular equation, that the time in which we are to determine the conversion is beyond the 20 minutes time given in the empirical rate equation, in which the equation is expected to work. So it's going to give us valid answers provided that those particular generalizations are followed. Okay, so that's it. So that's what it meant with those two generalizations from the empirical rate equation. Now, let's pick another problem. Any question in here? Okay, there's none. So let's go back to Levensville.
Ay, miss, excuse me,
Okay,
miss.
sorry. Okay. Yes, Josh.
So, ano ding answer din, miss? Ano ding answer, miss?
1.0.
Bali, ano
Your
mi,
solution would
1.0.
really, your solution would be this, of course, because you use the empirical rate equation. But at the end of the problems in kinetics, there's always a need for you to validate whether your answer is acceptable. Even though this is your answer, you will answer this one using this proof that the time the problem asks you to determine the conversion is beyond the 20 minutes based on the generalization for orders of reaction less than 1. So you're not going to answer this, but rather, anyway, this is not valid. This is not a valid value. You're going to answer 1.0. Conversion is already 100% after a half-hour run. Did I answer your question, Josh? Okay, sige. Now,
Yes, miss. Thank
okay,
you.
any question? Sa kinetics class yan, hindi lang ginashare sila nga simple nga masolve ka lang. Kasi hindi mo pag i-validate, mo answer kung acceptable siya o kung hindi. Because there are a lot of things in kinetics that you are to consider, not just a simple case of substitution to the formula that you have derived or either pre-derived by the author of the book that we're using. Okay, so I'll go back to Levenspiel. There aren't any question here. And let's pick another problem. Okay. This is one, the 3.6. It's easy. After an 8-minute run in a batch reactor, your CaO for a reactant which started with 1 mole per liter is 80% converted. After 18 minutes, the conversion is 90%. You are to find a rate equation to represent this reaction. So you only have actually a pair of information. Let me check. So if it's just a pair of information, meaning you are only going to equate two K values. Let me just show to you how this is done so you would know later on how to set up the equation for the two K values. So this is for number 3.6. Let me check if I have taken the picture. Okay, so it's included here. After an 8-minute run, so our given is for time equal to 8 minutes, reactant concentration starting with 1 mole per liter is 80% converted. So the pairing here is your XA here is 80% conversion. Now, after 34 minutes, 8 and 18. Sorry, I read a different problem. This is 8 and the other one is 18. So after 18 minutes, conversion is 3.6, 90%. So we're referring to the same reaction. So you are asked what rate equation represents the disappearance of the monomer. So it's speaking of the monomer rather. So you are asked for the rate equation. So that would be your rate law. Okay, now since you do not know the order of the reaction, you might as well start with the empirical rate equation. And the empirical rate equation, based on what we did here, I'll go back to the this one is for the half order. So we'll have we have to take it from the slide. Let me go back. So we will not have to derive again. Okay, it will not show class. Just show it without having to project. Here. Okay, so you have that. I hope you could see this one. So I will take a picture so we will not have to derive again. So we can save the time and then place it just on the whiteboard. Share. So this is I just shown to you the empirical rate equation. So we'll start with the new slide here. So you have number, where was that? Okay, here it is, so 3.6. So the formula for the empirical rate equation is Ca raised to 1 minus n minus CaO raised to 1 minus n over 1 minus n. But this is negative. We have derived it already. And this is Kt. If you want to determine the n by trial and error, as I've mentioned last meeting, the case for the two sets of values, that is the rate constants for the two sets of values here should be the same. So you should have a formula for the K. So your K is equal to CA raised to 1 minus N minus CaO raised to 1 minus N all over N minus 1 times the time. Now we will multiply, or we will substitute the values that we got here. Now again, you are given conversion. So there's a need for you to derive. Anyway, it's easy. So you just change the Ca to CaO, 1 minus Xa again, and this is 1 minus N, and this is 1 minus N. You have CaO raised to 1 minus N over N minus 1 times T. You need to change because your data, the provided data is in terms of conversion. CaO is equal to 1. So anything you multiply it with would simply be equal to 1. So I'll place it here. Our final working formula will be K being equal to 1 minus Xa raised to 1 minus N minus 1, because CaO is 1, all over N minus 1, and you have here time. You multiply the expression with time. Okay, CaO. If you want to have a more general representation, you can still have K over CaO raised to 1 minus N on the left side. And what's remaining here is the quantity 1 minus Xa raised to 1 minus N minus 1 raised to 1 minus N, which is still 1, all over N minus 1 times the T. Let me see. It's over T. If it's K, okay, it's not multiplication by T, so it's over T. Here, let me check. So you place the T in here, so it should be over T. Okay, so you have that. Now we substitute the value that we got for the information that we have. So you have new slide. I'll take a picture so I will not have to keep on going back again to this slide here. Okay, new slide. So your K is equal to 1 minus Xa raised to 1 minus N minus 1 over N minus 1. I'll place the T in here. So for our first set of information, the first set of information that we have for Xa, which is equal to 0.8, the time is 8 minutes. So we'll have here 1 minus 0.8 raised to 1 minus N minus 1 over N minus 1 times 8 minutes. Is that right? 8 minutes. 0.8 for 8 minutes. Right. So 0.9, that would be 18. So let's have this. So you have this slide here. So in here, of course, you have that. The other K, let's say I'll have this as K1. The other K, so K2, I will have 1 minus 0.9 raised to 1 minus N minus 1 all over N minus 1 times the time, which is 18. $18.90. So that's that. I'm just checking. 18 and 90. Okay, so this is your K2. So what would you do? It has to be that if we're talking about the same reactions, K1 should be equal to K2. So we will equate both of this expression that we have. So we have 1 minus, so we will simplify. So we will carry out the 1 minus 0.8, so that would be 0.2. So you have here 0.2 raised to 1 minus N minus 1 over 8 times N minus 1. We equate it to this expression here, the K2. This one. So you have a 0.10 raised to 1 minus n minus 1 all over 18 raised to n minus 1. Okay, you equated the two because we're talking of the same rate constant for a particular reaction. So our rate constant should not change. In the process, we'll get the, why is this not work? You'll get rid of this, the n minus 1. And what you will have is, resulting expression is 0.2 raised to 1 minus n minus 1 all over. I'll place this one in here. You have 0.1 raised to 1 minus n minus 1. The resulting expression that you have here, what am I doing? So 0.2, copied this copied, place in here. So I will have 8 over 18 on the other side. So 8 over 18. So this expression, let me go back. Let me have, so you have 0.2 raised to 1 minus n minus 1 over 0.1 raised to 1 minus n minus 1 is equal to 8 over 18. What's the value of that for 8 over 18? 2.25. I know I got this. It's the other way around. So what is the answer? 8 over 18.
0.44.
0.44. So you have here a 0.44. You cannot solve the n here analytically. Okay, the n cannot be solved here analytically. So you have to make a trial and error procedure here of finding the n. So if you have set, for example, n is equal to 1.5, because we cannot have an n here which is 1, because automatically that would be 0, and I have everything here 0 over 0. What's the value of the left side? Can you check? So 0.2 raised to negative 0.5 minus 1 over 0.1 raised to negative 0.5 minus 1. What's the value? Anyone? .57. Thank you. So if it's 0.57 and you have here 0.44, they're not the same. So you assign a new value. So let's say n is 2.0. So you have 0.2 minus, I'm sorry, 0.2 raised to negative 1 minus 1 divided by the quantity 0.1 raised to negative 1 minus 1. So your answer is 0.44 this time. Telling you that the order of the reaction is second order. So if you have a monomer and it's a second order reaction as stated in the problem, you're given a monomer, then your rate law will be something like this. RA is equal to K CA squared. You're asked for the rate equation, so this is not yet complete because you still need to determine the K, the value of the K. So the problem gives us the initial concentration, and we know that if we have, in particular, this is case, if I'm not mistaken, this is case 2 under second order. So you have a formula of 1 over Ca minus 1 over CaO being equal to Kt. Okay, let me share with you the slide. Okay, second order, case 2. That's our second order case 2. So this is the formula I have written there. Okay. So let's go back to our whiteboard. So this is it. So what you'll do, you'll substitute the values that you are given. So any of the pair of values will do. But the thing is, if you notice, we're given conversion. So you can change this one to XA over 1 minus XA being equal to KT. Still based on the equation that we have on the slide. So you can have here XA over 1 minus XA, but there's still a 1 minus a 1 over CAO, I forgot. So you have to place it there on the other side, on the right side of your equation. So this is to be multiplied to CAO. Okay, you have 1 over CAO here. So in the first set of data, you're given that there is a conversion of 0.8 for a time of, what's the time there? A conversion of 0.8 for the time of 8 minutes. So you place here 8 and CAO anyhow is 1. So you will have now a value for the K. Your value for the K will be 0.8 divided by 0.2 divided by 8. So that would be 0.5. So your K is 0.5. So it's liter per mole per minute. If it's a second order reaction, it's liter per mole per minute because our unit for concentration is mole per liter. Okay, so we go back to that, and this is our K now. So your final answer would be this. If you're asked for the rate equation, if the DE is speaking, if the problem is saying rate equation, then the rate equation should be like this, equal to 0.5 CA raised to 2. Or you can also write here the R sub A. When we speak of the rate equation, it's a differential equation. When we speak of the rate law, it would be good to write only negative R sub A being equal to 0.5 CA raised to 2. Okay, so this is the rate equation that is being asked in the problem. So nothing wrong if you write there the negative R sub A because anyhow, the equation is also present. And that's the negative dCA dt equal to 0.5 C sub A raised to 2. So that's how you use the empirical rate equation, trial and error in finding the N. After you determine the N, you solve for the K. Now you can check, you can validate actually class whether this value for the K that you got would still be the same if you're using the other set of values. So this one is for the 0.8 and 8 minute time. If you check with the, so if it's the 0.9 over point, of course, 0.1, and you will have here 18. You will use 18 on the other side because the time there is 18. You should be getting the same value. And that's 0.5. So let's have 0.9 divided by 0.1. That would be a 9 divided by 18. That would be 1/2. So it's still the same. So whether you use the first set or the second set, you'll still be arriving at the same rate expression that will represent the pair of information given in the problem. So the same rate law, the same rate equation. Okay? Now, any question? 10:57 is it 0.57, not 0.5? Why am I getting 0.5?
Pag-hinapan na, I think, miss.
Kahinapan ni
First.
Asher. Oh, okay. So, okay. So, I only read the chat now. Now, any questions here? I'll go back to 11 speed. Okay, what do we have next? It would have been good if we have reached 3.8, although I can give you the outline of how you're going to determine the solution for 3.8. Okay, I will just give you the direction on how you're going to solve for 3.8. So 3.8 goes this way. You are required to find the overall order of the irreversible reaction of hydrogen with nitrogen oxide, forming nitrogen gas and water. So the following data for a constant volume batch reactor is arrived at using equimolar amounts of hydrogen and nitric oxide. So you're using, or you're starting with an initial concentration of hydrogen and nitric oxide, which are said to be equal. Now, what is interesting about this problem is Levenspiel did not even give us a sample problem on how to deal with empirical data based on total pressure. So you have here half-life and you have here total pressure. But in the set of methods that you can use in determining the rate expression, this particular method, the half-life method, is part of it. So I will explain the half-life method. That way you will know how to process this one. So I'll go back to my slide on what is this half-life method is. Okay, it should be starting here. There's something wrong if I do it that way. So here it is. Will not anymore project it. The half-life method requires you, or the problem in this case, if it's going to use the half-life method, should provide you a pair also of data. The pair of data that the problem should be providing you would be initial concentration and the corresponding half-life for that particular initial concentration. So what you're going to do in this case is, though if you have the soft copy of Levenspiel, this K class is the average K. You could see here that this K average is equal to K over beta over alpha raised to B, and so on and so forth. This one is based on the stoichiometry, this one. Alpha and beta are the stoichiometric coefficients of A and B in your chemical reaction. Now, in our case, to simplify things, and this is how I suggest to my student always, that this K, which is average, represented as averaged by Levenspiel, or based on the coefficients, will be K. It's not K naught or K average, but will simply be the K, or that would be the rate constant for the given reaction. That way, this particular formula is comparable to the empirical rate equation, in which you have K, you have CaO and Ca, and of course with the time. The only difference of this formula with that particular derived formula for empirical rate equation, which is method 1, this is method 2, is that this time you're not given Ca versus T, but rather you're given CaO versus the half-life, telling you that the empirical data, the set of empirical data, was arrived at by starting with different initial concentrations of your reactants and correspondingly measuring the half-life based on those initial concentrations. And this will be the formula that you will be using for determining the K and the N. Of course, this one will also be trial and error if we are to, just like the first method, we are to equate that all K's for all pairs of values of CaO and T subscript 1/2 should be equal. Now, for example, you don't want to use the example. I don't want to do trial and error because that would take me a long time. Then you can approximate the value of the N and the K using the linearization process. What's the linearization process? You are to linearize this formula that is provided by Levenspiel. And after you have linearized it, use your calculator in finding the slope of the best fit line and the intercept of that particular formula. Now you will ask, what do you mean by that, Miss Ali? So I will take a picture of this and show to you how will you linearize this one and then deal directly with the pair of data that is provided in the problem without having to resort to trial and error, because that of course would entail a lot of time. When you do trial and error, it's okay with the case of the previous example that we have, because we're only given two sets of data to validate. So whatever works for the first set should work for the second set. Our problem would be if a given pair of data, would the given set of data will have, let's say, 5 pairs or 7 pairs of data. So you have to validate for all pairs of data that you have, and that will take a long time. So in this case, we will linearize the equation that is provided for the half-life method. But I have to emphasize, class, that this will only work if the problem gives you a pair of, so important that you understand that the data that is given to you is CAO versus half-life. You cannot use this method if the data that is given you is T and CA, because there's no way that you can find the different CAO for that matter, because the T versus CA data started with one particular CAO value. Isa lang ginaka-CAO value yung ginkuhaan niya or ginstartan niya. Whereas with this half-life method, several CAO values were used as a starting point, and then the half-life was measured for those CAO values. So this is what you're going to do. The formula, I'll show the formula. The formula is this. We will linearize this particular formula. So if we will linearize, there's a need for us to get or make this left side the argument of the ln, the same thing with what we have here. So everything, all of this should be the argument of the ln. What happened here? Okay, so I will have now the ln of the half-life being equal. So if I will use the ln here, automatically, class, this one will be, this is how it's supposed to be written. So you will see 0.5 raised to 1 minus n minus 1 over k times n minus 1. And I have here as CAO raised to 1 minus n. It's the entire expression now is the argument of the ln. And you've learned from your Math 11, EMA 101, that this can be written before the ln. So I can write this now as 1 minus n, the ln of, excuse me, you have 0.5 raised to 1 minus n minus 1 all over k times n minus 1 times CAO. Now, you may say, Miss, how about this one? No, I have this. I have products of this too. Now, this could be simplified further. I'll go to the next sheet here. You have ln of t 1/2. If you want to use the properties of ln when you have a product of two expression, you can also split these two. Like you have the ln of this only plus the ln of this, and this 1 over n you write before the ln. That way you will have a complete, shall I say, equation of a line. What do you mean by that, Miss? So this is what you're going to do. I have here the ln of CAO raised to 1 minus n. Split ko lang anay ha, plus the ln of, what was written there? It's quite long. 0.5 raised to 1 minus n. So I will have here 0.5 raised to 1 minus n minus 1 all over, I think, 1 minus n. I have very poor memory, so 1 minus n. Let me check. You have here k over n minus 1. suli. So, I will have negative K like that. Right? Now, you have ln of the half-life being equal to 1 minus n ln of CaO plus this entire thing. 0.5 raised to 1 minus n minus 1. So I don't want to deal with the negative. So this is n minus 1. This entire expression is the argument of this ln. If you notice here, the K and the N are all constant. So when we speak of a reaction, that K, the rate constant, and that order of the reaction is a constant. So then this must represent the B of your best fit line. This one is the M of your best fit line. This is your X, and this is your Y, which dictates to you that what you're going to do, the original CaO versus half-life data should be converted to the ln of CaO and the ln of half-life data. So the raw data that the problem gave you here, you are to get the ln of the data here. So all of the values that you have here, you have to take the ln. That way, you will have this new pair of data set. You will have new data set here. Now you will consider the pairs here to be coordinates of a point and get the equation of the best fit line. That way, when you have the slope of that best fit line right away, you can solve for the 1 minus n. So once you have the m, you can now equate that to 1 minus n. That will, of course, allow you to solve for n. When you already know the n, the value of the y-intercept can be solved because you will substitute the n that you got from the slope of the line. That will give you next the rate constant. Then after that, of course, you will have now the rate expression for your given set of data. So you will have now the rate law or the rate equation for your given set of data. Now, any question as to the procedure that I have discussed before I give you the direction on how you're going to process the problem that I have showed to you a while ago? Any questions so far? Okay, none. So everything is clear as to this procedure. Now, let's go to that problem which I presented to you a while ago. Okay, here we go. In the case of this problem class, you don't have one species, but rather you have two species, okay, with the same stoichiometric coefficients and with equal amounts initially present, okay? The same stoichiometric coefficients, equal amounts present initially. You can simplify actually the rate law for such an expression when you have equimolar amounts of species and the same stoichiometric coefficients for the reacting species. Now, let's say if you can think of how you're going to simplify that, okay? But there's a need for you. Why am I saying this? Because, let me annotate. If you're going to write the rate law in this case, since you have two species, natural thing for you will be K. If this is A and this is B, you will write CA raised to X and CB raised to Y. I place it X and Y because you don't know the order of the reaction. You cannot assume it's elementary, so you will write it that way. But I said you can simplify this because you are to use here, you have to use the concept that you have learned regarding kinetics of homogeneous reactions, especially having to do with stoichiometric coefficients, and you are to use this. Meaning for this problem, you're starting with the same initial concentration for A and B, where A and B are hydrogen and nitric oxide. Okay? Now, You may ask, Miss, what about this, Miss? It's giving us total pressure. There was no special mention in the book in Levenspiel on what particular formula you will use about total pressure. So I'm giving you a formula that you can use if you're given total pressure of the system. So that formula will be this. I'll write it here. You can take note of it because after this, I need to go to school because we have a meeting with the dean again. So I cannot upload right away the recording of this particular discussion. So you have this formula. The partial pressure of A is equal to the initial partial pressure of A minus A divided by delta N times pi minus pi sub O. Okay? Now, this is a formula that allows you to convert from the total pressure data here, and this total pressure data class is actually pi. From the total pressure data to partial pressure of A. With the partial pressure of A, you can get the concentration of A. You may ask, how can we get the concentration of A given the partial pressure of A? Of course, you have to assume ideal behavior. From the partial pressure info that you got from this formula, you will convert to concentration using your ideal gas equation. Now, you know that this pi is the total pressure of the system. What about the pi O? The pi O is the initial total pressure of your system. Initial total pressure of your system. Okay, take note. Initial total pressure of your system. What about the A? The A, this A is the stoichiometric coefficient of this A in your chemical reaction. So in this case, if A is hydrogen, then the small a will be 2. If capital A is hydrogen and you're after the partial pressure of hydrogen, this small a is 2. It's stoichiometric coefficient in the provided chemical reaction. What about the delta N? Okay, the delta N is equal to the sum of the stoichiometric coefficients of the products minus the sum of the stoichiometric coefficient of the reactants. In this case, your delta N will be 3 minus 4. And your delta N is negative 1. You get it? So now you know that you have delta N and now you have A and you have the different pi's in here. The different pi's corresponding to the half-life in second, and you have the pi O. Now you may ask me, what about Miss the pi O? The pi O, I'll give you a hint, is connected to the PaO. The PaO, again, is connected to this. Actually, your pi O is related to the equimolar amounts of A and B present. Now, I will be leaving you with this particular sheet work to do. You have until 11:59 p.m. to process this in groups. So you process this in groups this afternoon, this particular problem on how you're going to find the overall order of the reaction. So meaning you're only going to, in this case, if I presented it here as X and Y, the overall order that is being asked is X plus Y. So N being equal to X plus Y. Do you get it? You have a new formula to use, the formula that I have placed here, this one. I have explained the things that are in the formula. So pi are this total pressures. Pi O is the initial total pressure having to do, as a hint, with PaO, connected to the given in the problem that CaO and CbO are equal. you should be able to find the initial concentration of, or the initial partial pressure of A. If you know the initial partial pressure of A, this pi O can be expressed in terms of this initial partial pressure of A. You'll be able to get the PA. If you get the PA, you can solve for the CA, which you will, of course, plot using the procedure that I have discussed just a while ago. So CA versus half-life should give you the order of the reaction with this info here that is given. Now, any question? Any question? You may place it on the chat box if you cannot, if you do not have the phone. Any questions? So this will be your sit work this afternoon, due 11:59 later p.m. No question? Okay. So I think there are no more questions because you are silent. How many persons per... Diba nag-group na kamo sa inyo cell? Sa inyo nga mga... You had your groupings, right? You even submitted the problem sets already. This same grouping follows for this particular sit work. Your groupings, whenever I assign something collaborative to be submitted, will be the same for the entire semester. Di na ta mag-change grouping para hapo sa akong mag-follow up sa mga submissions. So the groupings that you submitted at the beginning of the semester will be the groupings that we will follow for all collaborative works, requirements, classworks. Any questions? To be submitted via Google Drive, isa lang sa inyo. Isa lang sa inyo. Hindi lang sa email. Kaya budlay yan kung mag-transfer from email to Drive. Unless nga budlay, so pwede gid niya sa email. Pero kung kaya man lang sa Drive, anyone in the group may submit the answer of the entire group in her Drive. Anyway, I have the info kung sino ang members ng isa ka group. Kung budlay, then have it in my email. Okay, but hindi na mag-submit, please sa messenger. Kay kagamay ka low gid sang quality sang ginasubmit nga mga screenshots to messenger kabudlay-budlay checkan. Ano ang file name is? Sitwork number 1. So I will place here, file name should be SW1. This is your first sitwork. Oh, wait. Sitwork number 1. That's the file name, Sitwork 1. One submission for the entire group. Any question? Some more questions? Okay, so I need to also prepare. I need to go to school. No more questions now? Okay. So thank you, class. If the internet connection tonight will cooperate, I may be able to upload the discussion for this. That way you can follow up right away during the long holiday. If you want to have a breather, and I think everybody needs a breather, then have a day or so to rest. But of course, there's a need for you to follow up what's being discussed in the case of your professional subjects, not just like kinetics. Okay, given the 1 hour synchronous time, or in our case, we even have 2 hours synchronous time, it's not even enough to cover everything that we need to cover. Okay? Sige. Bye for now, class. There's only 20 of you. I don't know where the other 11 is. probably having problem with connection as well. So thank you. I will stop sharing now. If I can spare time over the long weekdays, holidays, I can post recording of the next lessons. That way you can listen to them ahead and we can have problems in the class in our synchronous time based on those principles. Okay, bye for now, class.